Good morning. Let's do this. This. We can do the whole thing. No. Okay. So good morning. This is Calc 1. And today is what, the 20th or the 22nd? 22nd, yeah. Okay. So last time we finished with a little introduction to the idea of continuity or a continuous function. I want to pick up from there with our material today. Before I do that, though, a little announcement. Next Monday is a holiday. And since this is a virtual class, not an online class, we do have to still follow the college schedule, which means that we won't have a lecture next Monday. No lecture and nothing will be due. It's Memorial Day. And the homework 2 will be due on Wednesday instead. Nala, you do not eat that food, sorry. Kitty cat, that is not yours. No. No, baby. Okay, yeah, so the homework that you're working on right now, homework 2, would normally be due on Monday, right? That's what how our system works every Monday. I release the homework and it's due the following Monday at the start of class. But there is no class next Monday, so I don't feel like it would really be fair for me to have that homework come due on that day. So instead, it will be due on next Wednesday. Is there anything else like that that I'm missing? I don't think so. Simple enough, right? So then let's return to our discussion of continuity and continuous functions. So this is section 2.6. We all have some intuitive idea of what it means for a function to be continuous. But what we need is a rigorous definition. We need something that is defined in terms of mathematical operations. And kind of the whole reason we've been farting around with limits so far is so that we can discuss this concept of continuity. It turns out that the definition function f of x is continuous at some number a means that the limit as x approaches a of f of x is equal to f of a. And I want to talk about the different ways this can fail to happen. Last time we drew a picture and we kind of looked at some of the ways that this can fail. But I want to talk about it in terms of the notation here so we can get a little bit more comfy. So note for the statement above to be true, the following, we must have first, f of a has to exist. That is, a needs to be in the domain x. So that's the first thing that needs to be true. In order for a function to be continuous at some number, that number has to be in the domain of the function. If the function is not defined at that number, that is, if f of a does not exist, then I can't discuss whether f is continuous there or not. So in other words, a vertical asymptote or a hole automatically places where a function is discontinuous, because in both of those instances, f of a does not exist. The next thing that we need to have in order for this statement to have any chance of being true, this limit needs to exist. Right? So the definition of continuity that we have here says these two objects are equal to each other. And in order for that to be possible, the two objects need to exist, which might seem like something you could very quickly glance over and not care about, but we've seen multiple cases where either of these things fail to be true, and it's an important subtlety. So just like here, f of a must exist, and f of a existing means that a is in the domain of f. The limit as x approaches a for f of s must exist. What does it mean to say that the limit as x approaches a of f of x exists? Who can help me out with that? We've talked enough about limits now. What does it mean to say that this limit exists? Are you being good, Bubble? Yes, you're very handsome. I know it's Friday morning. It means that the left and right limits both are equal to each other, right? Yeah, let's see, what do we got in the chat there? Yeah, yep. So that is the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x. That's what it means to say that that limit exists, that the left and right limits are the same. And then the last thing is the obvious thing. The equality holds. Right, so all three of these things need to be true in order for the definition of continuity to be satisfied. In order for a function to be continuous, we need at some number a, we need the limit as x approaches a of f of x to equal f of a, which means that thing's got to exist, that thing's got to exist, and that thing's got to be true. That's the idea. And so if I ask you, is the function f of x continuous at 3 or continuous at 5, you need to check all three of these things. You need to check that f is defined at that number, whatever, 3 or 5. Then you need to check that the left and right limits match there. Sometimes you can do that very quickly with a graph. Sometimes you can do that very quickly with a theorem. And I'm going to give you several theorems today that will guarantee you sometimes when this is always true. And then you need to check that the limit is actually equal to the value of the function there. Any questions on this definition or this note? Any questions on the kind of notation or what it is that each of these statements is saying? The equality of this is true. Yeah. Okay then. So we think we have an intuition. We now have the technical definition. I'm going to draw for you a picture here that kind of tries to describe what it means to be continuous at A. So let me do it like, so maybe here's a number A. here's the graph y equals f of x. This is the x-axis. If you get closer and closer to that point on the graph from either side, the value of the function is what you approach, right? So this point on the graph here is the point a comma f of a, because its x value is a and its y value is f of a. And these arrows, remember, we kind of think of a little dude walking along the graph trying to meet up with his buddy. If he's walking from the left and his buddy's walking from the right and they're both getting closer and closer to the same thing, that's what it means for the limit to exist. How could this fail? Well, if this was an open hole here instead of a filled in dot, instead of a regular point on the graph, then the limit would exist, but f of a wouldn't be defined. So that's the first thing from the last page not being true. Or I could have this being an open hole here with like a dot up here. So the limit exists and f of a is defined, but f of a would be the y value up here, that filled in dot would be different from the value of the limit. So this is what we mean when we say f of x is continuous at a. How can it fail? Or what does it look like? To be not continuous? And there's a word for this. The word is discontinuous. So we call them discontinuities. What does it look like for this to not happen? I'm out of space here. So question mark. And there's a bunch of ways this can fail. So here's a graph of a very similar looking function. But this thing fails to be continuous in a few different ways. Right, so here at this hole, if this is like 1, this is like 2, and this is like 3. And here I'll call this the graph y equals g of x. At a equals 1, g of x is discontinuous why? Which of those 3 criterion from the previous page is not satisfied here? So I apologize for my bad art, right? This is just an open thing here. Can anybody tell me why g is discontinuous at 1?
Because there's a hole.
That's true. Could we be a little bit more technical about it though? Which of the three things from the previous page is not satisfied there?
G of 1 doesn't exist.
Yeah, very good. Right, right. Because there's a hole, what Angelica said is exactly correct. What Aubrey followed up with is a little bit more pointed. So g of x is discontinuous because g of 1 is not defined or does not exist. Good. Okay, what about at a equals 2? What's wrong there? Does g of 2 exist?
No. Yeah. These are one.
Yeah, g of 2 is
one on the top.
At this point. What about the limit? Does the limit as x approaches 2 exist? So if I sneak up towards x equals 2 along this graph, from either side, my y value is getting closer to the same thing. Let's use the space bar to temporarily unmute as needed to talk. That'll make life a little bit easier. So yeah, who wants to tell me? I see there's something in the chat here. Who wants to tell me what's going on at 2? Good, yeah. At a equals 2, the limit as x approaches a does exist. The limit as x approaches 2 of g of x does exist. But the limit is not equal to g of 2. G of 2 is the y value up here. The limit as x approaches 2 of g of x is the y value of the whole. Do you understand why?
So because they don't have the same y coordinate, they're not the same, and then that's why that happens.
Yeah, basically, I mean, if this y value right here is like 3, and this y value up here is like 5, then the limit here, this piece would be 3, and this piece would be 5. And those are definitely not equal, right? So remember, this hole is actually infinitely small. It's infinitely narrow. So no matter how close you get to 2, the y values aren't going to jump until you actually land right on 2. So as you sneak up and get closer and closer and closer to the x value 2 along this graph, your y values are just going to get closer and closer and closer to 3. So the limit as x approaches 2 of g of x, that's 3. But g of 2 itself is the y value all the way up here, which is 5. So even though the limit exists, and even though g of 2 is defined, they're not equal to each other. So in other words, it's the third criterion from that last page that fails at 2. What about when a is equal to 3? What's going wrong there?
Limit from the left is not equal to from
Exactly.
the right.
Yeah, the left limit here is different from the right limit. At a equals 3, the limit as x approaches 3 of g of x just does not exist. Because, like you said, the left limit is different from the right limit. Okay, so these are 3 of the gentler ways a function can fail to be continuous at a point. Right, when we approach from the left, we get this y value. When we approach from, when we approach from the right, we get this y value. And those are clearly not the same. This sort of behavior here, this is called a jump discontinuity. has a special name. And this behavior here, this hole, is called a removable discontinuity. This behavior here might have a special name, but in all my years of analysis, I've never actually heard it. I'm not sure. But this is called a removable discontinuity because I could come back and fill in the hole. I could define the function there, and I could define the function in such a way that it made the definition of continuity true. This I can't fix without undefining what G is, right? So here I can add some new information to fix the issue. Here I would have to delete some information and then add some information. So this does not count as a removable discontinuity. And this is called a jump discontinuity for the obvious reason, right? The graph makes a jump as you go over 3. The other type, which we talked about a little bit last time, is called an infinite discontinuity. Those are vertical asymptotes, right? A vertical asymptote, a place where your function explodes to infinity or explodes to minus infinity, those are called infinite discontinuities. So removable, jump, and infinite are the 3 types of discontinuities that I would like you to be able to classify and determine. Any questions on this little picture, this example, before we move away from it?
Sorry, I must not have unmuted myself. Removable discontinuity, is that where A equals 2?
Where A equals 1. A equals 1 is the removable discontinuity because I could remove the issue by just filling in the hole. Here, if I filled in the hole at 2, then this thing wouldn't be a function anymore, right? Because it would be sending the input 2 to 2 different outputs. But here I can fill in the hole without messing up the definition of a function, and then it would be a continuous function at A equals 1.
Cool.
Cool. Okay. So what comes next are several definitions and theorems. So I know I always say make sure you write down everything I write down on the .cam, but especially here, especially what I'm about to show you is important here for your theoretical completeness. So first, the definition I just gave you tells you what it means for a function to be continuous at a point. But in your previous classes, people refer to functions as being continuous functions, right? Like continuous everywhere. What does that mean? So we say the function f of x is continuous on the open interval AB if it is continuous at every number C in that interval. Right? So what does it mean to be continuous on an interval? It just means that the definition of continuity at a point is satisfied at every single point in this interval. So if you check one point at a time, you'll find that that definition is always true. If that's the case, then we say the function is continuous on the interval. Moreover, we say the function f of x is a continuous function if it is continuous everywhere in its domain. And there's a little subtlety here. There's a reason I'm using an open interval in this definition and not a closed interval. If I tried to define what it means for a function to be continuous on a closed interval, then I'd have to tell you what it means to be continuous on the end point. And the problem with being continuous on an end point of a closed interval is that I can't look at a two-sided limit. I can't approach from outside that interval. So we always do this on open intervals. There is a definition in your textbook. They talk about left and right continuous. So being continuous from the left, being continuous from the right. It's bogus, it's bullshit, it's weird, it's not useful. Calculus is all built around open intervals. You remember that was our day one discussion. Open intervals are everything. And that definition is just in your textbook like that in order to make some people happy. But in real life, we don't really give a shit about that stuff. So this is what it means for a function to be continuous overall. It means it's continuous everywhere in its domain. And this is what it means for a function to be continuous on an interval. It means that if you take any number from that interval, the function f will satisfy the definition of continuity at that number. And you can do that for every number in the interval. Theorem. All polynomial functions are continuous on negative infinity, infinity, which is their domain. Why is this true? Well, because if you take any number, any real number at all, try to picture the graph of a polynomial, it's always smooth. It never has any asymptotes or holes or jumps or any sort of weird shit. So if you want to take the limit as x approaches f of x, where f is any polynomial, so let's look at this here. I'll give a brief proof. Let p of x be a polynomial of degree n. Let c be a real number. So let c come from the interval negative infinity, infinity, be any real number. Then the limit as x approaches c of p of x. If you think back to our limit laws, this is the limit as x approaches c of this whole apparatus above, so an x to the n plus an minus 1, x to the n minus 1, plus down to a1x plus a0. We can use our limit laws to first break this up and take the limit of this piece, add it to the limit of this piece, add it to the limit of this piece, add it to the limit of this piece. So that's equal to lim x to c an x to the n plus lim x to c an minus 1 x to the n minus 1 plus lim x to c a1x plus lim x to c a0. And then each of these statements down here, each of these guys is something I know how to handle from my limit laws. Each of these is an easy limit to take. I can take each of these limits just by plugging in. So this is an c to the n plus n minus 1 c to the n minus 1 plus, hold on, no, not right now, a1 times c plus a0, which is p of c. Right? This is the formula for p of x, just with c plugged in. And now what you have is the limit as x approaches c of p of x equals p of c. So p of x is continuous at c. And that's job done, because c was just an arbitrary real number. So this shows that p of x is continuous at any arbitrary real number, which means p of x is continuous at every real number. And the big step here is using the limit laws, right? And we could be a little bit more verbose. An is a constant, so I pop this out, and then the limit as x goes to c of x to the n is c to the n. If you look back at last Wednesday's lecture, maybe last Friday's lecture, where we wrote out those 10 limit laws, those 10 limit laws, the first couple are exactly what we need to split this up, right? So the first limit law says the limit of a sum of a bunch of things, right? The limit of a bunch of things added up is the sum of each of those things with the limits taken individually. Then our second limit law said each of these constants could pop out. An, that's a constant. It's the lead coefficient for the polynomial p. An minus 1, that's a constant, so it could pop out. It could pop out. And then I think limit law 9 said that the limit as x approaches c of any power of x is just that power of c. So this constant an pops out, and then you get the limit as x approaches c of x to the n. So that's that constant times c to the n. This next guy, same thing. This constant pops out, you get the limit as x approaches c of x to the n minus 1. So that's c to the n minus 1, and so on. And by the time you finish applying all those limit laws, what you realize you have right here is p of c. It's what you would get if you just plugged c into this polynomial. So polynomial functions are continuous everywhere. I see a hand there. Yeah, what's up, Angelica?
Oh, thank you. Where it says under your proof, let's see, is that an E or equals when you're talking to the infinity?
Yeah. Okay, nope, sorry. This is a bit of notation. Here. The symbol, I'm glad you asked, because this is a symbol that I am always tempted to use, but a little bit nervous to use because I know not everybody knows it. So if A is a set and X is a variable, this is read as, this means X is an element of the set A. So when I say let C be in negative infinity to infinity, this is read as let C be any element of the interval negative infinity to infinity. All right, so this symbol right here is read as element of or in. So here I'm just saying C is in the interval negative infinity infinity.
Cool, thank you.
All right. Yeah, it's a useful symbol. Okay. Any other questions about this theorem? If the proof doesn't sit super well with you, don't panic or be upset. That's pretty normal in a calc class, especially in a calc 1 class, because you guys haven't been taught how to prove things or what proofs really are. But you should see this as an argument that shows that polynomials really are continuous. That's the idea. And then if you want to try to digest the argument in its detail, I'd be happy to help you with that. But the upshot is that if I hand you a polynomial and I ask you, is this continuous at 5? Is this continuous at 3? Is this continuous at pi? The answer is always yes. Polynomials are continuous everywhere. Our next theorem is kind of similar in style. So let me, yeah, like that. if f of x and g of x are continuous at A, then so are f of x plus or minus g of x, f of x times g of x, f of x over g of x, as long as g of A is not equal to 0, and the composite function f of g of x. So in other words, this says if you glue together two continuous functions in any of the ways we know how to glue functions together, the result is another continuous function. Sums and differences of continuous functions are continuous. Products and quotients of continuous functions are continuous as long as the quotient is defined. And this is a cool one. The composition of any two continuous functions are continuous. This is one of those theorems that is a classic to make a student prove, but not in this class, in the next level calculus class. So if you take advanced calculus or intro to real analysis, you'll be asked to prove this theorem. And it's not a hard proof. But we're going to take it for granted because I'd have to go through a separate delta epsilon argument for each of these, and nobody knows delta epsilon arguments right now. So this has some consequences. There's a corollary. Rational functions like r of x equals p of x over q of x, where p and q are both polynomials. Are continuous everywhere q of x is not equal to 0. Why is that a corollary of the previous theorem? Well, because the last two theorems said that polynomials are all continuous, and then this theorem says that if you divide two continuous functions, you get a continuous function. And a rational function is exactly what you get if you divide two polynomials. So since every polynomial is continuous and ratios of continuous functions are continuous, rational functions must be continuous, except where the bottom is 0. And you see this in the graphs, right? You guys have studied graphs of rational functions quite a bit. Oh, by the way, I posted something under the modules. If you want to look a little more in depth at how to graph rational functions, the discussion we had the other day, take a look at the review material resources in the modules on Canvas. I posted one extra thing there and also a bunch of stuff from chapter 2 that you might find useful. So rational functions are continuous because they are ratios of polynomials, and polynomials are continuous. One more theorem, one or two more theorems along these lines. And then we'll look at some example problems. All known transcendental functions. So all the transcendental functions you know are continuous everywhere in their domain. So what is a transcendental function? Well, it's like sine, cosine, natural log, exponentials, all of the trig functions, exponential functions, and log functions that you have met. These are all continuous everywhere they are defined. So this means you may have noticed that the front of your textbook says early transcendentals. That means they introduced these functions early on. So sine x, cos x, these guys are continuous everywhere because their domain is all real numbers. Tangent x, we know that he's not continuous everywhere. He has vertical asymptotes at odd multiples of pi over 2. But odd multiples of pi over 2 are not a part of the domain for tangent. So as long as you stay in the domain for the tangent function, that is, you stay away from pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, as long as you stay away from those numbers, he'll be continuous. Secant, cosecant, all the trig functions. Also, their inverses. These are all continuous everywhere in their domain. Also, your exponential functions like e to the x, 2 to the x, 1/3 to the x, those are continuous. And their domains are all real numbers, so they're continuous everywhere, just like polynomials. Who else do we have? Natural log, other base logarithms like the common log, or log 2. So this is pretty much all of the transcendental functions that we know at this point. And these are all continuous everywhere in their domain. Right? Now the domain of the natural log, or the base 10 log, or the base 2 log, doesn't include any negative numbers. These are not continuous at like -2 or 0, because their domain is only the positive reals. But they are continuous everywhere on the positive reals. These guys have domain all real numbers, so they're continuous at every real number. These guys have little domains. The domain for the inverse sine function, does anybody remember that? Inverse sine function has domain -1 to 1, and he's continuous everywhere there. Same's true for inverse cosine. Inverse tangent function has domain all real numbers, and he's continuous everywhere. Sine, cosine have domains all real numbers, they're continuous everywhere. Tangent we already discussed, just stay away from odd multiples of pi over 2. So that's it for the theorems for now. I'm going to have one more theorem, one more important theorem for you before the end of the day, but before we get there, I want to look at 1 or 2 little example problems. All right. Let's do this guy. We'll also do, well, we'll go through one at a time. I'll write them as we go. That way we can keep our notes organized. Okay, so can we identify the location of any discontinuities for the function f of x equals x squared plus 3x minus 5 over x squared plus 3x plus 6? So first, can I cancel the x squareds? There's an x squared upstairs, there's an x squared downstairs. Do they cancel?
No.
No, they don't, right? Because we have to be able to factor in order to cancel. The only thing we can cancel top to bottom are factors of the top that are shared with factors of the bottom. For the same reason, I can't cancel the 3x. So there's nothing like that that I can do. What can I do here? Think back to the theorem that came right before this one, the theorem in corollary.
Like FOIL?
Yeah, well, we want a factor, right? If I need to find out where this function is discontinuous, what kind of function is this?
Rational function.
Good. Yeah, this is a rational function. So by our corollary, or corollary, you can say it either way. Our corollary, f of x is continuous everywhere the denominator, x squared plus 3x plus 6 is not equal to 0. So to figure out the location of any discontinuities, we need to find out where the bottom is equal to 0. So we factor the bottom. X squared plus 3x plus 6. Let's see, does this factor? So I need two numbers who multiply to 6 and sum to positive 3. Are there any two such numbers?
Negative.
I don't think there are, right? 6 can be written as 6 times 1 or 2 times 3. And since both the 6 and the middle term here are positive, that means that both of the numbers we would use to factor would have to be positive. But there are no two positive numbers that multiply to 6 and add to 3. 2 plus 3 is 5, and 6 plus 1 is 7. So this is equal to 0 if and only if we use the quadratic formula. X is equal to negative b, so that's negative 3 plus and minus the square root of b squared, it's 3 squared, minus 4 times 1 times 6, all over 2 times 1. So that is, this thing is equal to 0 if and only if x is equal to negative 3 plus and minus. That's 24. 9 minus 24 is negative 15 all over 2. So these are not real numbers, are they? Right? The square root here has a negative underneath it. So x squared plus 3x plus 6 is not equal to 0 for any real number x. Therefore, or thus, f of x is continuous. We would say f of x is continuous everywhere except at these numbers, but these aren't real numbers. So f of x is continuous at every real number. Right? Because there are no real numbers that make that denominator 0. Let's try one more. We're going to try several more. We'll build up slowly.
Mr. P, can you
Yeah.
help me? Can I look at something from the page? Thank you so much.
Yeah, no problem. Sorry, if I ever am moving too quickly or I turn a page or something like that, don't hesitate to do exactly what she just did. You can ask me to hold off for a second. Are there any other questions or comments on this one? Do you see what we were doing and why we got the result we did?
So the answer is all real numbers.
We have to be careful about what the question was asking. So they asked us to identify the location of any discontinuities. And what we said is that f is continuous at every real number. So if you wanted to finish this up, we would say there are no discontinuities.
Meaning the graph doesn't break in any way.
Yep, exactly, yeah. Yeah, this is a continuous function, i.e. this is a function that is continuous everywhere. At every real number, this function is continuous. So there's no holes, no jumps, no nothing. If the bottom did have a real number which made it 0, the type of discontinuity that a rational function usually has, there's two possibilities. You can either have a hole, if there's a factor that cancels top to bottom, or you can have a vertical asymptote, which is an infinite discontinuity. But since this denominator is never 0, there are no discontinuities. Okay, so let's try a few more like this. Same question, identify the location of any discontinuities for the function f of x equals let's do this guy. So my aim is to identify the location of any discontinuities for this function. And what we want to do first here is factor the bottom if we can, or find out where the bottom is 0, because again, this is a rational function. So it will be discontinuous only where the bottom is equal to 0. That is, where x squared minus x minus 2 is equal to 0. And this one I think does factor, right? Here I need two numbers that multiply to -2 and add up to -1. Those would be x plus 1 and x minus 2. So that bottom is equal to 0 if and only if x is equal to -1 or x is equal to +2. And I have a sneaking suspicion I know what a few of you are thinking. Oh, never mind. Yeah, right. Yeah, so in the last step, we had to use the quadratic formula because we couldn't factor. The polynomial downstairs, the quadratic downstairs didn't factor, so we used the quadratic formula instead. Here, the downstairs does factor. And we find that the bottom is equal to 0 at x equals 1 and at x equals 2. Therefore, f of x is discontinuous at x equals -1 and at x equals 2. And for the purposes of this question, we're done. So we don't have to write anything else here. But I would like to ask, what kind of discontinuities do you think we're looking at?
Are there two vertical asymptotes there?
Oh, that's kind of the question, right? Yeah, are these both vertical asymptotes, or are there something else going on, or what's up?
Or no, because if we factor out the top, then something cancels, creating a hole.
Good, perfect, you got it exactly. So one of these is a hole, and the other one is a vertical asymptote. Which one is the hole?
-1, I think. I didn't do the work though.
Yeah, exactly. Yep, the hole is at -1. really quick, let's take a look at the graph. Never a bad idea. Okay. So here's the graph. And if we look at the line x equals 2, that vertical line, you'll see that's the vertical asymptote. But also, if you look way down over here, at x equals -1, oh, I'm not going to show it. There is a hole there. Yeah, there it is. Boom, undefined. Because there's a factor of x plus 1 top to bottom that cancels. So if I had to classify these two, I would say this is a removable discontinuity, and this is an infinite discontinuity. X equals -1, that's a hole, so that's a removable discontinuity. And x equals 2, that was an infinite discontinuity, or a vertical asymptote. Here at Santa Fe, our Calc 1 class doesn't emphasize classification of discontinuities. But I know many of you intend to transfer to UF for your programs, and in their calc sequence, this is a big deal. So that's why I'm taking the time to mention it. All right, let's play around with one or two more of these. Let's look at sine x plus the inverse tangent of x plus the natural log of x, all divided by x minus 3. I would like to know, I think usually somewhere around 50 to 60% of Santa Fe students aspire to transfer to UF, but of course not everybody does. Many people are here for their own programs, many people aim to transfer somewhere else. Many people are here to do a 4-year degree even at Santa Fe, like accounting or nursing stuff. So there's lots of things, but I know that a meaningful percentage of people do intend to go to UF. So that's why I mentioned that. So here's another function. I'd like to answer the same question. Let's find the location, i.e. the x values, of any discontinuities. This is not a rational function. Sine x, inverse tangent of x, and natural log of x, those are all transcendental functions. In other words, the top here is not a polynomial. So I can't apply my theorem on rational functions, but I can apply my theorem on combinations of functions. By our theorem on combining continuous functions, f of x will be discontinuous only at the x values where sine x, the inverse tangent of x, the natural log of x are discontinuous, and where the bottom is equal to 0. So we're laying out a strategy. We say, I'm going to find the discontinuities for this big weird function by finding the discontinuities for this, finding the discontinuities for this, finding the discontinuities for this, and also watching out for anything that makes the bottom 0. So let's start with the sine function. Where is the sine function discontinuous? I want to say sine x is discontinuous at da 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 da, therefore f is discontinuous there. Where is sine discontinuous?
So would it be outside its domain -1, 1, therefore you write wrong.
So the domain of the inverse sine function is -1 to 1. Well, what is the domain of the original sine function?
All real numbers.
Mm-hmm. And sine is continuous everywhere in its domain. Its domain is all real numbers. Therefore, sine x is discontinuous nowhere. So he doesn't contribute any discontinuities to f. What about the inverse tangent function?
Same, nowhere.
Good. What about the natural log function?
All negative numbers?
This is a little bit subtle. So the domain of the natural log function is just the positive numbers.
From 0 to infinite?
Yeah, I would say he is discontinuous at x equals 0. And undefined, we'll leave it at that. So he has an infinite discontinuity at x equals 0. Remember, the graph of the natural log function looks like this. So he shoots down to -infinity here at 0. So he'll contribute a discontinuity at x equals 0. And he also forces the domain of f to be just the positive reals. And then finally here, the bottom is equal to 0 if and only if x minus 3 is equal to 0, if and only if x equals 3. Therefore, I would say two things. First, f of x is discontinuous at x equals 0 and x equals 3. And is continuous. This is going a bit beyond what the problem asked for now, but I'm wanting to make sure we're all comfy. And is continuous everywhere else on its domain, which is 0 to 3, unioned with 3 to infinity. So sine and arctan don't contribute any discontinuities. The natural logarithm contributes a discontinuity at x equals 0, and the denominator contributes a discontinuity at x equals 3. Remember when you were in college algebra or pre-calculus, you talked about finding domains of combinations of functions. You had to take the overlap of the domains of the functions that make it up. This guy's domain is all real numbers, this guy's domain is all real numbers, but this guy's domain is just 0 to infinity. So the domain of f, we're starting at best with 0 to infinity, and then we also have to punch out 3 because he makes the bottom 0.
It says continuous everywhere and then blank on its.
else. Everywhere else, sorry.
Thank you.
So he's continuous here, and he's discontinuous here. And both of those discontinuities are going to be infinite discontinuities. Right? There's definitely no factor of x minus 3 in the top that will cancel. So the x minus 3 downstairs gives us a vertical asymptote at 3. And the natural log has its own infinite discontinuity at 0. So if this piece goes to negative infinity, so will the whole thing. There's one more type of question that I want to play with regarding continuity. And then I'm going to give you the last theorem for this week. Still doing okay. Not like that. Not like that. We're going to find a good one. Where is it? Continuity. Mm-hmm. 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 No. Oh, wow. Your book doesn't have any of these. Damn. There's a large family of really cool problems that I want to at least give you one of. But there aren't any here. Okay. So I'll have to make it up. That's okay. I'm going to need just 1 second to think here to make sure I craft this well. We'll do it like this. And then okay, so for what value of k is the function defined piecewise by x squared if x is less than 1, and kx if x is greater than or equal to 1, continuous at a equals 1? Or I could say continuous everywhere, because each of these pieces is continuous on their own. So the only place this piecewise function could fail to be continuous is the place where I'm trying to join them up. Do we feel like we understand the question?
Not 100%.
So let me
Yeah, no, me neither. I don't understand.
Let me look at some examples of functions like this. Here's the function I get if I plug in k equals 3. What's the graph of this function look like? Well, if x is less than 1, then this function behaves like x squared. So there's the first piece where this is 1. And then f of x equals 3x, what does that look like? Well, that's a line going through the origin with slope 3. So he would look like this, right? And this is definitely not a continuous function. This would be 1, 2, 3. Or if I plugged in k equals -1, then that would look like this. Because if x is less than 1, then this thing behaves like y equals x squared. If x is bigger than or equal to 1, it behaves like y equals -x, which is a line through the origin with slope -1. So neither of these are continuous everywhere, right? They both have a problem at 1. This is what I get if I plug in k equals -1 to the formula from the previous page. This is what I get if I plug in k equals 3 to the formula from the previous page. So what I need to do is find the value of k that allows the function to be continuous.
So like the little gaps.
Right, how do I get rid of the gaps? So I'm sorry, if I called this section 2.6 earlier, this is section 2.5, continuity. So I want to return to the question at hand, right? I know that piecewise functions can be a little bit weird, and I'll just show you how to solve this. This is an important family of problems. Figuring out how to take a function that has an extra parameter in it, that number k there is called a parameter. What we need is the limit as x approaches 1 of f of x to be equal to f of 1, right? That's what it means for a function to be continuous at 1. And 1 is the only place where this function could have a problem, because that's where I'm trying to stitch together the two different functions. That's what this piecewise function thing is. How many, can I use the React tool here real quick? And I'm going to come back to my gallery view. How many people feel like they got a good treatment of piecewise functions in their pre-calculus class? How many people feel like if I give you any piecewise function made up of functions you know, could give me a graph of that function? So you can use the thumbs up reaction tool if you feel comfy with that, just so I have a feel, because I know that not every pre-calc class treats piecewise functions very well. Okay, so let me make a little note here. I'm going to add something to the resources page on piecewise functions, so you guys can take a look at that if you feel like you got shortchanged a little bit there, because I know a lot of folks do. Pre-calc's a busy class. There's a lot of material in it. And this is section 2.5. Okay, so this guy, we need him to exist, which means we need the limit as x approaches 1 from the left of f of x to be equal to the limit as x approaches 1 from the right of f of x. So we're going to calculate those two limits and see what we get. F of 1 I can get from the definition of the function here. F of 1 is what you get when you plug in 1 for x. And this says, okay, if you want to plug in 1 for x because 1 is greater than or equal to 1, you use this formula. So f of 1 is k times 1, which is just k. The limit as x approaches 1 from the left means I'm going to be plugging in numbers that are closer and closer to 1, but are smaller than 1. So I'll be using this piece. This is the limit as x approaches 1 from the left of x squared, which is 1 squared, which is 1. And the limit as x approaches 1 from the right means I'm going to be sneaking up on 1, but using numbers for x that are slightly bigger than 1. So that's these guys, meaning this guy. So this is the limit as x approaches 1 from the right of kx, which is k. Now, in order for the limit to exist, I need the limit from the left to equal the limit from the right. One of those is 1, the other one is k. So we need k to be equal to 1. And if we do plug in 1 for k, do we get something that satisfies the definition of a continuous function? So in other words, is f of x defined by the piecewise rule x squared if x is greater than, or sorry, if x is less than 1, and 1 times x if x is greater than or equal to 1 continuous? Let's see.
Sorry, can you go back real quick? Oh, you got it.
Yeah, so the limit as x approaches 1 of f of x, if you look from the left, that's the limit as x approaches 1 from the left of x squared, that's 1. If you look from the right, that's the limit as x approaches 1 of x, that's 1. And f of 1 is what I get when I plug in x equals 1, so I'll be using this guy, that's 1 times 1, is also 1. So yes, if k is equal to 1, then f of x is continuous at a equals 1. Hence, continuous everywhere. Okay. So because your textbook doesn't have these problems in there, at least for now, you don't have to stress about them too much. But this is a good family of problems where I give you a piecewise function with some constant in it, and I ask you for what value of that constant will this function be continuous everywhere. The pieces x squared and kx are both continuous on their own. So the only way for things to go wrong is for us to stitch them up in a way that is discontinuous. And we saw that if k is -1, then we end up with a discontinuity. If k is 3, we end up with a discontinuity. But if k is equal to 1, the definition of continuity is satisfied because the limit of f of x is 1 and f of 1 is 1. So the limit is equal to the value of the function. That's the big thing. Okay, we are a little bit short on time, and there's one more theorem I want to present to you from 2.5 before we leave. So if you'd like to spend more time thinking about this problem, you can come see me in office hours today, or check out the video once it's up. I'll have it up early this afternoon. You can pause it, hang out, chill. The last thing I want to show you is what's called the, not mean value theorem, we're not ready for that, the intermediate value theorem. And I want to give it to you exactly as your book gives it to you. Basically, it says that a continuous function has an image, is the word we would use in a higher math class, which is an interval. But the way your book says it, if the function f of x is continuous at every point in the interval AB, and n is any number between f of A and f of B, then there is a number C coming from the interval AB, and I guess it could, yeah, coming from the open interval AB, such that f of C is equal to n. This can look a little bit intimidating at first, but if we go through it bit by bit and think about what it's saying, it's actually very, very intuitive. So here's my function f. Its domain includes the closed interval AB. Here's the point A comma f of A. So up here, this y value is f of A. This y value down here is f of B. So if you pick any number n in between these guys, you will find a corresponding number down here, C, between these guys, so that f of x or f of C is equal to n. Another way to say this is you can't go from being above a line to being below that line without crossing the line. So since over here we start out above this line, and down here we end up below this line, since the function is continuous, you have to have crossed the line. That's the way most people think about this. So if you start above a line and end below the line, you had to cross the line. That's the idea. The only way for this to fail is for f of x to be discontinuous. The only way to go from above the line to below the line without crossing the line is for there to have been a discontinuity of some sort. Does that make sense? So this is called the intermediate value theorem. And one of the things we can do with this is prove the existence of solutions to certain equations. So I'd like to use the intermediate value theorem to show that this equation has a solution somewhere between 1 and 2. the solution. So here we go. So we're going to let f of x be 4x cubed minus 6x squared plus 3x minus 2. F of x is a polynomial. Therefore, it is continuous everywhere. F of 1 is 4 minus 6 plus 3 minus 2. So that's negative 2 plus 1 is negative 1. And f of 2 is 4 times 8 minus 6 times 4 plus 3 times 2 minus 2 is 12. Therefore, f of x equals 0 somewhere between x equals 1 and x equals 2 by the intermediate value theorem. Right? F of 1 is less than 0. F of 2 is bigger than 0. So somewhere in between x equals 1 and x equals 2, f of x had to be equal to 0. We started below 0. We ended above 0. So somewhere in between 1 and 2, we had to be equal to 0. And that's it. That's all they asked us to do. We don't have to find the solution. We just have to show that a solution exists. I start below the x-axis. I finish above the x-axis. So somewhere I had to cross the x-axis. Why? Because we're continuous. Does that make sense? Okay. So the last topic that I intended to talk about this week was limits at infinity and horizontal asymptotes. It looks like that's going to have to wait until next week, and that's okay. Before I let you go, though, I do want you to think about one other thing. So like I said, don't stress about the homework. Finish up all the homework that you can. It's not going to be due on Monday because Monday is a holiday. So next Wednesday, we will begin our discussion on limits at infinity, and I'll make sure to adjust the homework so you don't have anything come due on Wednesday that you're not prepared to handle. But one last thing to think about before I let you guys go. I want to introduce you to two new functions. One of them is called d of x. It's the Dirichlet function. And this is good review for those of us who want practice with piecewise functions. The Dirichlet function is equal to 1 if you feed it a rational number, and it's equal to 0 if you feed it an irrational number. So for example, d of 0 is 1, d of 1 is 1, d of 2 is 1, d of any integer is 1 because all integers are rational numbers. Also, d of 1/2 is 1. d of 3/4 is 1. d of any fraction, right, of any rational number will output 1. But d of pi, that's 0. d of the square root of 2, that's 0. d of e, that's 0. d of 1 over the square root of 3, that's 0. Because all of these inputs are irrational numbers. Where is d of x continuous? And where is it discontinuous? So this is a famous fun problem. Dirichlet was one of the first people to formalize the mathematics of calculus. So Leibniz and Newton, they did a really good job of coming up with the ideas that would allow us to do calculus, but they didn't really understand what the fuck was going on. Dirichlet understood what the fuck was going on. And the way he came to understand it was by thinking about really weird functions like this. The graph of this function is a very strange thing. It's like a sprinkling of dust up here at 1, and an even thicker sprinkling of dust down here at 0, because it turns out there are a lot more irrational numbers than there are rational numbers. Very strange graph. And I'd like to ask the same question for a slightly modified version. But for this guy, he's equal to x if x is irrational, and equal to 0 if x is rational. The graph of this function is also a bunch of sprinklings of dust, but now the irrational sprinklings of dust are along the line y equals x. And the sprinklings along the bottom are at all the rational numbers. So some really, really weird functions here. The Dirichlet function and this kind of modified Dirichlet function. Both good ways to learn to think about piecewise functions and also incredibly weirdly behaved functions when it comes to continuity. Turns out the second guy is continuous somewhere. There is an x value at which the second function is continuous. I'll let you think about why, but this first guy, he's not continuous anywhere. He's really weirdly behaved. Okay, that's where I'm going to leave it today. If you haven't typed anything in the chat so far, please go ahead and just type here or something so I have a good record of attendance. And once you have done that, you are welcome to head out. Remember, no class on Monday. Monday is a holiday. So I will see you guys next time on Wednesday. Please make sure you finish up all the homework that goes through 2.5. Anything from 2.6, I'll go ahead and move to next week's homework. All right, I hope you guys have a pleasant rest of your day. And if you need to see me, remember there's an office hour this afternoon.